So Turan, can you hear us? Well, we can hear you. So just a sec. So I guess we need to turn up your volume. Could you speak again, please? No, we can't hear. So let me check. Vocês conseguem? So Turan, could you please unmute your microphone and try again?
Oh,
Okay.
I'm sorry, could you repeat that?
No,
I hear you, but somewhat weakly.
no, now we can hear you. So thanks. So now it's our pleasure to have Turan Birol joining us remotely from Minnesota, and he's going to talk about oh, now have the pleasure of having Turan Birol joining us from Minnesota, and he's going to talk about atomic and unit cell multipoles and altermagnets. So please.
Okay, thank you very much. I assume that you can hear me well, otherwise you would stop me.
Yes,
So,
yes.
yeah. Hi everyone. So let me start my timer here because I won't be able to see the chair when I go over time. But as I understand, this is 40 minutes, so 35 plus 5 or so.
Yes, 35 plus
okay.
5, yes.
Yeah. So I want to thank you very much for the invitation to present in this workshop. And I apologize from everyone that I'm not there. I really wanted to be there. There was something that came up in the last minute, unfortunately. But anyway, here we are. So today I'm going to tell you about our recent work on atomic and unit cell multipoles in altermagnets. And this is work that is done to a large extent in collaboration with Rafael Fernandez, who's there among the collaborators, and one of my students, Luca Burarelli. And here is a quick outline. So as I understand, I'm the first person to actually talk about altermagnets in this workshop. So I will start with a brief introduction, then I will show you some symmetry discussions and also some first principles results on the magnetic multipoles in altermagnets. And I will conclude by talking about the observables a little bit and propose piezomagnetism as a way that can actually probe altermagnets order with quite a lot of detail. Okay, so altermagnetism has a relatively short history. It was, I think the word was coined less than 5 years ago. And it's hard to put, of course, a single paper to the pedestal saying it started this whole thing. As I include here, there are multiple papers that are around 2020 that were influential. But I think this paper sort of requires some special attention. So this was a first principles paper, again, where they proposed that ruthenium oxide, RuO2, which was thought to be an antiferromagnet at the time, is a new type of material such that it actually displays a spontaneous Hall effect, something like an anomalous Hall effect, without having an overall magnetic moment. So even though it's not a ferromagnet, it displays this. And they showed that when you do DFT, you can see that spin up shown in red and spin down shown in blue bands are split, even though you wouldn't expect this type of exchange splitting when there is no overall ferromagnetic order, and the spin density in real space as a non-trivial pattern as well. So this paper in some ways is actually a bad starting point because as of 2025, as of last year, I should say, we know pretty well that there's no spontaneous Hall effect if you don't have an overall magnetic moment allowed by symmetry, and bulk ruthenium oxide is not even magnetic, like it's not even antiferromagnetic. Nevertheless, some of these ideas like this non-relativistic spin splitting between opposite spin bands, etc., are interesting enough that this nevertheless jump-started this whole area. And yeah, so this is what I will be talking about today. Now, instead of thinking about what leads to a splitting, I think it's a better way to think, it's better to think about this problem by asking, well, what makes the bands degenerate? So if you have silicon, for example, and you do a DFT calculation, you get spin up and spin down bands, and they are degenerate everywhere. So this condition is satisfied at every K, energy of the upspin and downspin band states are the same. Whereas in a general magnetic material, or when there's no inversion symmetry, you can end up with equations, situations like this, where there's no degeneracies. So in terms of the symmetries, we usually casually say the reason that in a non-magnetic material bands are degenerate is the time reversal symmetry, which I denote. I follow the crystallographer's notation here, which I know physicists usually don't like, so sorry, please bear with me. But I denote time reversal with 1' and inversion with 1 bar. So time reversal flips both K and spin. So it doesn't set a degeneracy at a single K point. Inversion flips K, but it doesn't flip spin. So it does not make the two bands at a single K point degenerate either. However, if you have the combination of these two, so I'm not saying you have to have inversion and time reversal separately, but if you have inversion followed by time reversal, which we call anti-inversion, if you have this combination as a symmetry, then you flip the spin, but you don't flip the K, and then you actually have this band sticking together everywhere in the Brillouin zone. And I will just in passing say that you can also have some argument with translation here, but that part is not necessary for this talk, so let's ignore the right-hand side for now. So what I will do now is I will show you some spin patterns and discuss what symmetries they have connected with their band dispersions in reciprocal space. So for this, I will consider pseudo-scalar spins, as in like I'm sketching spins as like pointing up, and I will call them upspin, downspin, but they don't need to point along a specific crystallographic direction. So for now, we ignore magnetocrystalline anisotropy. So if you have a ferromagnet on, say, 2D square lattice, all the spins are parallel, and if you apply time reversal to this, then you get all the spins pointing in the opposite direction. They are all down now. And there is no crystallographic operation. So there is no way to displace the atoms in a way that this state on the right goes back to the states on the left, to the state on the left. So in a ferromagnet, time reversal is broken, and there is no way to undo it crystallographically by displacing atoms by applying a crystal symmetry operation. So there's nothing that sets a degeneracy for the bands anywhere in the Brillouin zone. In an antiferromagnet, you have alternating up and down spins. And when you apply time reversal, if you look carefully, you get a different state because, say, the atom on the corner is up here, whereas it's down here. So each individual atom is flipped. But on an infinite crystal, you can do two different things. You can either apply inversion to the positions of the atoms around one of the bond centers, or you can just displace the whole crystal by one lattice spacing, and then every blue atom would go back to being blue in the original state. So in an antiferromagnet of this type, where you have time reversal followed by either a translation, lattice translation, or inversion, B symmetry elements, and either one of those combinations, either this anti-translation or anti-inversion, is actually sufficient to ensure that in the reciprocal space, bands are degenerate everywhere. Now, altermagnets are by nature more complicated materials, and you cannot quite represent an altermagnet with a single atom tight binding model even. So what is important in an altermagnet is that its starting crystal structure, even without magnetism, has a lower symmetry. So if you think of any exciting material, I'm pretty sure any material being discussed in this meeting, they are never elemental materials. I mean, there's nothing wrong with iron, etc., but you don't get unconventional magnetism in such simple materials, right? So usually you have some ligands, some oxygens, some chalcogens, some anion that is not magnetic itself, but it provides a lower symmetry environment to the magnetic ions, the transition metals typically. So let's consider a material that has a crystal structure like this, where I have in gray some metal cation that will host magnetism, and it's surrounded by some anions, oxygens maybe, that have a different symmetry in that there are shorter bonds and longer bonds, and the orientation of these bonds are alternating. So the crystallographic unit cell, what you would see when you do XRD, is actually this shown in this thin gray lines, is larger. It contains two metal atoms now. Now, on top of this, I impose the same magnetic order, antiferromagnetic order that I had before. But the interesting thing is, in the previous case, antiferromagnet doubled the unit cell size. Here, the unit cell size was already larger, so antiferromagnetic order here doesn't break translational symmetry. Okay. Now, if I apply time reversal, everything is flipped. But the thing is, this one now is a different state, because if you look at the state on the right, for example, every red atom, every upspin is in a rhombus that has the long axis along this direction, whereas on the right, the upspins have the long axis along the perpendicular direction. So you cannot just do inversion or something as simple as a translation to go from the state on the right to the state on the left. However, if you rotate the structure on the right by 90 degrees around one of the centers of the unit cell, then you go back to the picture on the left. So again, this is like an antiferromagnet in the sense that a crystallographic symmetry can undo the effect of time reversal, but it is not like an antiferromagnet because that symmetry is not translation or inversion. Now, this is what I will call an altermagnet. And what happens in these altermagnets is that due to the nature of this symmetry, you actually get bands stick together, bands being spin degenerate in certain parts of the reciprocal space in the Brillouin zone, and they will be non-degenerate in certain objects. And this non-degeneracy is what distinguishes them from antiferromagnets. Okay. So people have been studying the symmetry of antiferromagnets for a while using these magnetic space groups. So there are about 2,000 of these, 1,700 of these. And you can classify them into different groups. And there are many studies. I think this was one of the earlier ones that were extensive, which undergo materials databases, look at the magnetic space group, which includes the symmetry of the crystal structure and the magnetic order, and see what materials show this type of splitting or not. Now, this approach is completely fine, and it is essentially complete. However, so if you go after this and borrow this book is about 4,500 pages. So nobody wants to deal with 1,600 different types of magnetism, right? Because classifying that is possible but quite tedious. So what I will do instead is, instead of considering different magnetic structures, I will tell you about different magnetic order parameters, which is much easier to keep track of. So there are two different ways to approach the symmetry of symmetry of anything, essentially. So, but here in the context of magnetic materials, I can either work with magnetic space groups, which classify the symmetry of the magnetic phase, or I can work with the non-magnetic phase, so consider the symmetry of the crystal itself, and then consider the magnetic order parameter. Now, this order parameter is, I'm just following the Landau's definition here. It's what breaks the symmetry, and the order parameter explains every broken symmetry. Mathematically, and this is not something that I will get too deep into, but just as a concept, the mathematical way to classify different ways to break symmetries correspond to different irreducible representations, or IRREPs, of the space group or the point group. So this is just tabulated. So what you can do is you can go to either online database or textbook, and you see all the lists of different ways that say a cubic symmetry can be broken magnetically or by something else. And in the context of altermagnets, the only IRREPs, irreducible representations, that I am interested in are IRREPs that break time reversal, because I'm interested in something magnetic, but that don't break inversion. Because if something breaks both time reversal and inversion, then the combination of time, so if I have a quantity that's odd under both of these, then it will be even under their combination. So it will be even under anti-inversion. That would keep all the bands degenerate. So that would be an antiferromagnetic order parameter. Okay, so what I did is as I said, you can just go to the database. I went to the crystal server. This is shot from.
Sorry, you just have a question here.
Yes.
Yeah, a quick question. You pointed out very nicely that you do not break translation invariant because it's already broken in the example that you gave, right?
Yes.
And why isn't it then enough to just look at the irreducible representation of the point group? Why do I need to include space groups?
That is a great question, and actually, what I will be doing is exactly that, because in the constraints of a 40-minute presentation, I cannot do everything with the space groups. However, if I want to say anything more general regarding real materials, I would, even though point group representations is completely sufficient for most materials, I still need to consider the space group representations to be safe, because one can devise examples where you have a antiferromagnetic order, so some magnetic order that is not at the gamma point, that by itself doesn't lead to altermagnetic splitting, but it might be inducing, through different types of couplings in the free energy, an altermagnetic order as a secondary order parameter. So in that sense, the space group representations are more general, but you are right in that I think in every example I will consider actual point group will be completely sufficient.
Thank you.
Thank you. Thanks. Yeah, and by the way, if anyone else has any questions, please feel free to interrupt, because I think I will have enough time in the end too. Okay, so this is the so-called character table. You don't need to know what a character is for the point group. So I will switch the point groups for now. Of OH, this is M3 bar M. So this is the cubic point group with all the mirrors and whatnot. This is what, for example, a perovskite would have if it was in high temperature cubic phase. And what's important is that here you see there are 10 irreducible representations. Here the superscript minus refers to the representation being odd under time reversal. So these are the 10 unique time reversal breaking representations of this point group. So this is the only 10 ways to break time reversal symmetry for a cubic system which preserved or which had all the mirrors to begin with. Now, among these, there are these subscripts U and G. These are gerade, ungerade in German. So G are even under time reverse, even under inversion. I'm sorry. U are odd under inversion. Now, as I said, I'm interested in only inversion even irreps for altermagnetism. So I crossed 5 of these, and I left with 5 irreps that may be possibly altermagnetic. But one of this is the magnetic dipole. This is the ferromagnetic order parameter. So I crossed that out too. And I am left with 4 options. So these 4 are the only 4 types of primary altermagnetic orders that can exist in a cubic crystal. So this is really nice, because if I was supposed to, list the magnetic space groups, there would be like hundreds perhaps, or tens at least. But with the irreps, I only have 4. And this enables you to, this is what we discussed in length in this paper, for example, derive K-space expressions. So derive like a K.P expressions for different band structures in materials where you have these different types of magnetic orders. You can pick one, and you can plot the band splittings in reciprocal space. And if you have a real material with this type of magnetic order, maybe nickel disulfide is an example, I'm not sure, but anyway, I'm sure there are some, then you really observe this type of band splitting where like the sign flips at different parts of the Brillouin zone. And my title had multipoles. I'm not going to talk about multipoles a whole lot, but basically, we mostly work with dipoles, of course, but if you read Jackson, which I'm sure there are some students there who are suffering through Jackson nowadays, or like there are more modern discussions too, you can talk about dipoles, quadrupoles, octupoles up to nth order, and you can do this for charge. You can do this for spin as well. So this is a dipole, then this would be a quadrupole, this would be an octupole, and so on. And if you also consider toroidal fields, so the magnetic field lines that form a loop in like a torus type thing, in a crystal, of course, you would have discrete rotations only, right? So if you have this rotated magnetic dipoles, then this gives rise to a different type of multipole that's called a toroidal multipole. And what you can do is these ones also break the symmetry. So these can also be classified using the irreducible representations of the point group. And it turns out that the dipole, of course, is the same irrep as the ferromagnetic order parameter, right? So it is what ferromagnetism is after all. And the altermagnetic order parameters show up either as some toroidal multipoles, which I will ignore for now, but or as the magnetic octupole. So this is this like nice description in the sense that like an altermagnet is just a more complicated version of a, if you want ferromagnet, instead of having a dipolar order, you have a magnetic octopolar order. And this was acknowledged by, I guess, Nicholas Spalding for the first time, but this is gaining more traction nowadays. Okay, now, can I see these multipoles in real life? And, you know, in real life, meaning for me, real life is DFT, right? Some first principles calculation. And the answer is yes, but this requires a little bit of thinking, even though it's a somewhat trivial calculation. So what I show you here is manganese difluoride, which is not a particularly famous compound, but it has the same magnetic structure that was proposed for ruthenium oxide. So it was a nice material to connect with all the work, all the theory that was proposed for ruthenium oxide originally. You have the purple manganese ions that have opposite spins on the corner or in the body center. This is the primitive unit cell with 2 manganese ions. And we usually think of magnetic orders just in terms of the metal cations. But what you can do is, again, you can use crystallography tables to see what other atoms, the fluorine atoms shown in gray here, can do in terms of magnetism. Now, fluorine has a closed F shell in manganese difluoride, so it's not an ion that would want to develop a magnetic moment. However, when you do DFT, sometimes you find some small, like 0.05 Bohr magnetons maybe, but something non-zero, something reproducible magnetic moments, even on these anions. So there's something called a Wyckoff position, a Wyckoff site, Wyckoff letter, if you will, that is assigned to every atom in every structure. And there's the magnetic version of that as well, which says that, for example, in manganese difluoride, the manganese ions are on Wyckoff site 2A, which means that they will come in pairs. There will be one manganese at 0, 0, 0 corner and one manganese in the body center. And they are allowed to have magnetic moments, but they have to be along the Z direction and they have to be opposite. Now, the interesting thing about fluorine is that it's on the 4F Wyckoff site, and just based on symmetry, we see that the fluorine ions are also allowed to have a magnetic moment. It has to be along the Z direction, and it has to also cancel. So this is a small thing, like who cares about a 0.05 Bohr magneton density on fluorine, you may say. Now, the interesting corollary of this is fluorine magnetic order. You can pick any random point in your unit cell, and that is also assigned a Wyckoff site. So the black ones are these 8J Wyckoff site. There are no atoms there, but there's a spin density, right? Because electrons occupy the whole unit cell with some density. And at these points, symmetry is low enough that you also have the X and Y components of the spin density that form a pattern like this. So really, if you care about the spin density, not atomic magnetic moments, but the magnetic moments at arbitrary points in space, every magnetic material is actually a non-collinear magnet, because there are always some low symmetry enough points in the unit cell where symmetry is low enough that the direction of the magnetic moment is not constrained at all. And doing DFT, you can actually plot this density. So what we did is we performed DFT calculations, including spin-orbit coupling, and we plotted isosurfaces of the spin magnetic moment density, so essentially spin density, throughout the unit cell. And the density itself is hard to plot, so we plotted the isosurfaces. So this is the isosurface of the MZZ component of spin. You have a positive spin near the positive spin Z, so spin up near the center atom, and you have a negative one around the corner atoms. And the density looks almost perfectly spherically symmetric because manganese has a closed F, well, half-filled F shell here. Now, when you do the same thing for X and Y components of spin, the numbers you get are much smaller because bulk of the magnetic moments are along the Z direction, but you get nice flower-like patterns, I call them, but strictly speaking, these are G-orbital-like patterns that look like this. So if you integrate, for example, the X component of spin's density around any atom, the red and blue positive and negative cancel each other. So the total net magnetic moment on an atom is still along the Z direction, but as a function of position, it has this interesting nodal structure, and the same along Y. Now, if you do the math, you can project this onto different cubic harmonics, tesseract harmonics. So you get non-zero contributions from the L equal to 2 and L equal to 4. So the D and G like multiples from this. So what you see by I here is actually just this component. So this looks like this GYZ cube function. And that gives rise to a 32 pole, which is called Dotria conta pole, apparently, pattern around each atom. But these little lobes are not exactly the same size. So when you do the math, there's actually a non-zero contribution from this DYZ octupole as well. Now, this result is interesting because this material is considered to be a D-wave altermagnet. So people have been talking about this octupole all along. And if you look at the reciprocal space, actually, that's really what you see. But apparently in real space, if you look close enough, you get this 32 polar contribution to be more visible, more dominant in certain sides of the certain directions of the spin density. So how this appears in response is, well, what I will get into later on. Okay. Okay, I am doing fine in time. So we discussed about space versus point groups. So let me do a little bit for, this is somewhat technical, so I don't think this will be the most popular part of the talk, but for the few people who are perhaps more into this group theory thing. So the thing with the space group representations is that you can use them. So if you represent the magnetic order as a proper space group symmetry breaking order, you can use it to predict what atomic multiples, what atomic representations are allowed to exist, and whether they will be in phase or out of phase between different manganese ions. So the procedure we follow is called subduction. This is pretty standard, like if you read Dressalas textbook or so. This is used commonly in different contexts. It's not used as much in magnetic orders, but it really, I will use uncommon words perhaps, but if you know this type of stuff, this is actually a trivial calculation. So the symmetry of a manganese site, so the collection of point operations that leave a single manganese's environment invariant is D2H, it's MMM. And you can do the subduction calculation, which would tell you that if you have this M gamma 2 plus order parameter, which is what manganese difluoride has, this would induce on each manganese site only one irrep of the local group, and that would be B1G minus. So on each manganese, whatever multipole you see, this could be a spherical distribution of the spin along Z or this 32 polar weird distribution of spin along X, they all transform as the same point group irrep B1G. Now, this was a puzzle for us because the subduction analysis tells two things. One, B1G is the only thing that should exist on each atomic site, but two, the relative phase between two different atomic sites of manganese has to be the same, right? So since it's the same irrep both on the site and on the space group, everything has to be either in phase or out of phase. But you see that these dipolar things, so spin up, spin down along Z, they are opposite signed. But when you look at this 32 pole or certain octupoles, they are actually in phase because they add and they give rise to, so what's on the right gives rise to the altermagnetic order. So what happens is that actually you have these non-symmetric symmetries. So non-symmetric symmetries are screw and glide axes. So these are not point operations. So these are not just simple rotations, but these are rotations followed by a translation that is half in itself. In the context of manganese difluorides, if you rotate the crystal by 90 degrees around this black line, and then take half a step along the Z direction, that would take this atom, bring it here, and move up. So the corner and center atoms would exchange, flip places, and that would leave your crystal and that would leave your magnetic order invariant, turns out. Now, what matters, what this means is that if I have a multipole on the corner atom, I have a 90-degree rotated version of the same multipole on the atom in the center. But not every multipole is equal in the sense that some of the multipoles I showed you just look like spheres, right, in the spin density, so they are invariant under a 90-degree spin rotation. But some of the ones I have are, they get a minus sign under a 90-degree spin rotation. So if you write different magnetic multipolar expressions, as I did on the left, and these are dipoles, octupoles, 32 poles, they are all the same irrep, so they are all allowed on manganese. but they have different CIFR eigenvalues. So some of them change sign under the 90-degree rotation. And it's those that change sign under this 90-degree rotation, which is part of this screw, this non-symmetric symmetry, they, when you use a global coordinate system, remain invariant and they add up in the unit cell. And that's what you see when you plot the band structure. You see whatever is in phase and adds up and gives rise to this Altermagnets quarter. Okay, and you can explicitly calculate these on two different atoms. So it's red and blue here. And as you see, the in phase ones are on top of each other, whereas the out of phase ones have the opposite sign on the two atoms and they cancel. Okay, finally, in the last 6-7 minutes, excuse me, I will talk about macroscopic observables because, you know, altermagnetism is all fun and games, and I think it gave us, the first principles people interested in DFT calculations, etc., a lot of interesting band structures to look into. But we really need to connect with the experiment in a unique way. So it turns out that people were really excited about this Hall effect measurements in altermagnets early on. But I think there's a, well, I think the jury is still out, but there's a growing number of people, myself included, who think that this Hall effect is not really a good way to probe altermagnetism. And it would be better to find a unique probe of altermagnetism that can distinguish it from more traditional forms of antiferromagnetism. Okay, so for this, I'm going to, well, let me give you a spoiler. First, I'm going to consider something called piezomagnetism. So piezoelectricity is relatively well known, though, well, I'm used to giving similar talks in engineering audiences. They, you know, in engineering, piezoelectricity is used so often that even undergrads know all about it. So just as a reminder to us, though, piezoelectricity is a linear connection, so a bilinear term in the free energy expansion, if you want, between stress or strain, I will use strain, and the macroscopic dipole moment, so the polarization in the unit cell. So there are certain materials which, when you compress along some direction, accumulate some positive and negative charge on the opposite surfaces, which corresponds to a polarization, a dipole moment in the unit cell. It is a rank 3 tensorial quantity, so the ith component of P is proportional to the JK component of strain. So remember, strain is a rank 2 tensor, and its product with this lambda IJK, the piezoelectricity tensor, which for some reason has shifted up in my slide. Sorry for that. So the symmetry of the crystal imposes constraints on the form of this lambda. So there's a simple prescription to see how a rank 3 tensor transforms under some symmetry operation of the crystal. And as a consequence, you don't have piezoelectricity in every crystal. Actually, if you have something that's inversion symmetric, so if you have a centrosymmetric crystal, it cannot be piezoelectric. And bulk of the non-inversion symmetric crystals, non-centrosymmetric crystals, are piezoelectric to some extent. Piezomagnetism is the equivalent effect. Instead of a electric dipole P, I'm considering a magnetic dipole, however. So when you compress a material, there's a spontaneous magnetic moment that emerges. And when you change the sign of the strain, the magnetic moment flips. So this distinguishes it, this bilinear behavior distinguishes it from effects like magnetostriction, which might have, which might connect external magnetic field with a strain induced in the sample, but those effects are usually not, they don't change sign under, for example, when you change the sign of the magnetic field, but piezomagnetism does, okay? So it has been around for a while. Zieloshensky himself worked on piezomagnetism. It's weak, so it was not extremely popular until at least recently. There weren't many studies. But mathematically, you also represent it with a rank 3 tensor, so pi ijk. And now this pi would be constrained by both crystallographic symmetry and the magnetic symmetry. And the spoiler of what I will tell you in the next few minutes is that antiferromagnets are not piezomagnetic, but altermagnets are piezomagnetic. Okay. All right, so how can we prove that at a hand wave away is by taking the piezomagnetic tensor and looking at its symmetry properties. So we often use something called the Young symbol to represent such quantities. So for the piezomagnetic tensor, this is the relevant symbol. What this says is that there are 3 V's, so it's rank 3, it has 3 indices. it is in the square bracket, so it is symmetric under the exchange of the last two indices. So if you exchange JK, strain stays the same, piezomagnetic tensor stays the same. And AE means that it is time reversal odd, it is a magnetic effect, but it is inversion even in this context because, well, both M and epsilon are inversion even, so pi needs to be inversion even anyway. Okay. So what you can do is, okay, well, I was supposed to have a reference here, but anyway, so we have a paper earlier this year where we showed that you can take arbitrary response tensors and you can expand them in terms of the irreducible representations of the point group as well. Again, this is not like in the context of group theory, this is a well-defined procedure, but the practical importance of this is the following. So it's easy to take a point group or take a space group and predict what components of the response tensor, say gamma, would be non-zero, pi, I'm sorry, not gamma, would be non-zero, would be equal to each other, etc. But the question that I want to answer is not about the symmetry broken phase. I want to work with the symmetric phase, so the high temperature phase, and I want to assign different order parameters to different components of the response tensor. So what this tells me is when I do this expansion in M3 bar M, if I have a magnetic order parameter that transforms as one of these irreps, one of these representations, then there will be components of the pi, the piezomagnetism tensor, that will be linearly proportional to these. And the interesting thing here is all the irreps I have here have minus sign above, so of course they need to break time reversal, but they are all G, they are all even under time reversal. So what this says is, in the cubic case at least, the four irreps that give rise to piezomagnetism are not antiferromagnetic. One of them is ferromagnetic, T1G minus. Ferromagnets are piezomagnets, sure, but the others are all altermagnetic. So there's this one-to-one connection. Every altermagnetic order, except for one, there's one single exception, gives rise to a piezomagnetic tensor component and unique tensor component, and none of the antiferromagnetic ones do. And here I do the same thing for the tetragonal case. Again, there's a one-to-one correspondence with the altermagnetic orders and the orders that give rise to a non-zero component in the piezomagnetism tensor. So manganese difluoride has B2G minus order in this language. This comes in with a coefficient 2 in front, which means that there will be two components of the piezomagnetism tensor that will be non-zero and independent. Okay, and you can make an analogy here about how every ferroelectric is a piezoelectric, every ferromagnet is a piezomagnet, but there are piezoelectrics that are not ferroelectric. Similarly, there are piezomagnets that are non-ferromagnet that are not ferromagnets, and those are altermagnets. Okay, so this is the form of the piezomagnetic tensor. As I said, there is one component, this blue one, that's equal to each other that appears in two places, and then there's the other one that's independent. And what you can do is a simple DFT calculation. Now you can take manganese difluoride, you can strain it, you can change the lattice parameters by hand. And if you do things right, only shear strains should give rise to a magnetic moment. And each shear strain, YZ, XZ, XY, give rise to a magnetic moment in the plane, in the direction normal to the strain plane. So here are the results. If you look at the X component of the magnetic moment, none of these four different types of strain give rise to any magnetization. If you calculate the Y component of the magnetic moment, this blue line, XZ, gives you this one, right? Gives a magnetic moment linearly proportional to strain. Again, changes sign when strain changes sign. And along Z, you get a different number, so the vertical axes are different. Okay. And interestingly, you may ask the effect of spin-orbit coupling in this. This blue component, for example, if I plot it as a function of spin-orbit coupling, because in DFT I can just change the coefficients, right? It goes down to 0 when spin-orbit coupling is turned off. Okay. Now, this is I'm running out of time, so I will rush through this, but this is like what goes down to 0 when spin-orbit coupling is turned off. So what quantity depends on spin-orbit coupling is not something you can answer using the symmetry that is represented in the magnetic space groups, because any symmetry operation in the magnetic space group actually leaves the spin-orbit coupling L dot S invariant. But you need to actually take one step further and people use something called spin groups, which is an interesting story. So this was essentially a 60-year-old abandoned area that was rediscovered after this altermagnetism came out. And now, like, there are some recent papers which do everything consistently. So spin groups are again becoming useful. So the key observation is that if I rotate the spins only, not the atoms, not the crystal structure, but the spins only, by an arbitrary angle around the z direction, around the outer plane axis, it's a symmetry of the system because the spins are around z already. But that operation sets spin-orbit coupling to 0, because if S is rotated by itself, then this dot product cannot remain invariant. So if I apply that constraint to the tensor pi, then I find that the xyz and yzx components have to be 0 if spin rotation by itself is a symmetry, which is equivalent to saying when spin-orbit coupling is off. And that is really what explains why this piezomagnetic tensor is piezomagnetic response is suppressed, but only these components are suppressed when spin-orbit coupling is turned off. Okay, I think I'm slightly over time already, so I would like to thank you very much for your attention and conclude by apologizing again that I cannot be there in person.
So thank you for this really nice talk. Questions?
This is a beautiful talk, Turan. I have a question. I mean, so you focused on the piezomagnetism and sort of wrote off the case of magnetostriction, but the magnetostriction is going to be just as informative. I mean, it would be when you reverse the direction of the field, the induced strain would have the opposite sign. So I think it would be just as good. And we have very sensitive ways of measuring induced strains through X-ray diffraction. So I just wonder why you particularly focused on the piezomagnetism. Thank you.
That's a good question, and I should say that when I write TOEFL, I do it as like a spoiled theorist who doesn't have any idea like what is an easy experiment and what is a hard experiment. It turns out that piezomagnetism is actually not that easy either, right? So the nice thing with piezomagnetism is it's unique to altermagnets and ferromagnets, but it is necessarily 0 in pure antiferromagnets. So if you already know the magnetic structure and you do magnetostriction measurement, I think that's completely fine. And the information that would come from there, as you said, would be very valuable. However, it will not be an effect that's unique to altermagnets or ferromagnets only. So you cannot distinguish between antiferromagnets and altermagnets just based on the magnetostriction, I believe. So I think in magnetostriction, what you have the first order in magnetic field and second order in strain. So, or is it the other way around?
The other way around.
So,
the other way around.
Like in the term you write in the free energy expansion would be second order in one of the two quantities. So it would not, one of the two quantities would be insensitive to the sign, essentially.
I had a question on the absolute magnitude of the piezomagnetic coupling, right? I mean, formal, which is 10 to the minus 5 is not the biggest of numbers. And do I understand correctly that the reason why it's so small is that ultimately what makes the difference that there is piezomagnetism in the first place is the presence of the fluorine in the system. But there is such a tiny moment induced net on the fluorine sites that this seems to be, well, then the coupling to the cubic with 0 elastic properties is exceedingly small. So do I see this correctly? And what can we learn from it in getting a different material that would have maybe a larger effect?
That's a great question, and one thing I should say is so these are our own calculations. So I'm not like I don't want to be offensive against my own work, but the numbers here are not even to be taken too seriously in the sense that there are different parameters. The U parameter in DFT, that's a famous one, right? But also temperature that sensitively affect these quantities. So manganese difluoride is actually one of the materials which show a much smaller effect. I wanted to show it in particular here because I think that's where we got the best, cleanest example, as in like the numbers, the plots on the right are almost perfectly linear. But there are two things that play here. One, the blue component, this one, that's 10 to the minus 2, that depends on spin-orbit coupling. And spin-orbit coupling is weak in manganese difluoride, right? Fluorine is light. It's right next to oxygen. Manganese is 3D. So anything that depends on spin-orbit coupling will be small in this material. Now, interestingly, the other component, this red one, the ZXY component, that is even smaller, even though this one doesn't depend on spin-orbit coupling. And the reason that this is suppressed is actually Luttinger compensation. So this is an insulator. It has a very large band gap, multiple electron volts. So anything that would change MZ, that would change the occupation on the two sides and lead to a magnetic moment, that requires electrons crossing the gap. And at zero temperature, that wouldn't even happen. Here we have like a 5 millielectron volt or something temperature on the calculations that gives rise to this. But I think if you want to go somewhere where you would have a larger response, depending on the component, for some components, a larger spin-orbit coupling would, of course, lead to larger tilting of the magnetic moments. But for other components like MZ here, where spin-orbit coupling is not necessary, I think you need room in the Hilbert space where electrons can be excited freely. So having a metal would give rise to a much better result. So we have results in like there's cobalt difluorides, which also is an insulator, but you can fictitiously turn it into a metal in DFT, even though that's not relevant to real life. But if you do that calculation, that metallic system, you get MZ that's like a couple of orders of magnitude larger than this one. So spin-orbit coupling and metals is the short answer to your question, I guess.
So one last question here.
Well, very nice talk, very clear for me. Are you aware about real experiments about under uniaxial strain or something like that in this kind of sample, or that's just a proposal?
We do have some experimental collaborators working on that. Here at the University of Minnesota too. There's, for example, Martin Graben here, who does uniaxial strain.
Okay. Here is a collaborator. Okay. Okay. But please continue.
It turns out that this is an easy experiment to propose, but experimentally it's a bit more challenging to have both large amounts of strain. Like here, I go to 3%, right? So, well, look at it, my students, which is experimental, not trivial, and do a sensitive measurement at the same time. But I think there will be many works in the next few years where these measurements will be presented in Altermagnets.
Okay, thank you.
Okay, so let us thank the speaker again.
Thank you very much.
And now we close this first afternoon section and go to the coffee break and resume in 20 minutes.